Hello, how are you?
Hello, doing good. How are you?
Good, thank you.
Excuse me, Professor.
Yes,
I was
I
wondering if you could submit the homework as a MATLAB script, or if we
sure.
took pictures of the script and sit that in.
Yes, like a PDF.
Yeah.
Yeah, absolutely.
Okay, thank you.
Sure.
Do we have a quiz today?
Yes.
Still due at 9?
I don't know yet.
Okay, today is
Depends on whether we are going to have, it's a very short one that I would give you, but if we don't have time to do it, I will leave it up until 9.
okay. Today is September the 11th.
I know. I was going to talk about that.
Dr. Day,
Yes, hi.
I had a question regarding the project weekly submissions.
Yes.
So it doesn't submit it as a group. So do you want each person to submit it?
No, just one from, I will, you should only submit one. And thank you for reminding me, I need to create a submission for, I need to go back and change it so you can submit it as a group. I have the opportunity to do that and not individually.
Okay.
So, all right, so you don't have, only as a group, you submit it, only one, and then it goes automatically, the grade is gonna go to all of you.
Professor,
Yes.
do you have any template for weekly reports of the project?
I don't have a template, but I will give you some guidance today, and I will, when I send you the, I will send you an email. I don't want this to be very extensive. For the first ones, I would like to see how they look. I don't want them to be more than a maximum under any circumstances. I don't want it to be more than 4 or 5 pages. Less is better. You know that. I mean, if you can respond to everything correctly within half a page, I would do that. And but I would throughout this semester, I will never go over 5 pages, no matter what. Not even for the final or the midterm report. So,
I see. Also, we need to answer the question at the top of the project, right?
yes.
Or do you want it to be a bullet point format or in paragraph?
A bullet point, you know what it is. They say enough to respond accurately. Saying too much is not worth it. If you need to say more to explain why, say that. I mean, but brevity is always the right thing to do. And so be brief and be complete as much as you can, optimize between the two.
But you don't want it as like an essay format, like an introduction.
I don't want essays. No, not essays.
All right, that's what.
Bullet format is great if that's what you're asking me. Yes.
Yeah, thank you.
Yeah. Okay, I think we need to start today, and exactly like Zehin reminded me, it did not remind me. In fact, I've been thinking about this the whole morning. Today is September 11th, and I know that maybe you were very young at the time it happened because it's 19 years ago. But I have to tell you that I was in San Francisco going to a conference at Livermore when it happened. And it's a day that we should always remember because 3,000 people, if not more, died without knowing why. And So every year that is happening, I remember about it. It was a major shakeup for our country. In fact, I saw it on TV when the second, in real time, when the second plane hit the tower, and it's like it's something that remains with you for the rest of your life. It was a horrible incident by all regards, and so it got us into a major war for many years. Trying to bring justice to the people who died. And it just, terrorism is such a horrible thing. It destroys communities, it destroys societies, destroys everything. And we had to fight it for many years. But I just wanted to tell you, I was at the time at the University of Michigan, and we had a number of students from the business school who were doing internship because the classes are starting a little later at the time, and they were doing internship, so they died in there. It was a horrible thing. So I just wanted to remember the people who died for no reason. But other than this, I wanted to just say that even you did not live those horrible moments, you should always remember that, it's democracy. It's something that we have to defend at any cost. And a lot of people died then. And since then, just to bring justice and protect democracy in our country. And democracy cannot exist with fear. You cannot allow terrorists, to create fear in the society. And so, in any case, a lot of us learned a lot. A lot of people lost their own people, members of their families, parents, mothers, daughters, brothers, and fathers, and many family members. And there was the one thing that I remember when the tower fell down. That was another tragic moment. There was a whole group of the firefighters who died, about 120 people. There were fathers and sons and brothers in that group. They all died together, and it was a horrible thing, trying to save other people. So this is not something you forget, and I don't want you to forget it either, even you did not live it through. But in any case, I just wanted to say a few words, and I felt the need to say that. So let's look forward at this moment, hopefully that we will not go through an experience like this again. And I don't wish it to anyone to go through an experience like that. So what I wanted to do today is share my thoughts about the last, let me see, 1 second. I wanted, you don't see that. I need to do this again. Start broadcasting. For some reason, I lose it. Okay. All right, here we go. So before we start with the practical implementations, I would like to share some things that I've learned from experience, obviously, and from designing circuits. So you have a better understanding of why some solutions are more practical than others. And I would like to discuss that. Also, I would like to discuss why some passive components that we use in high frequencies do not necessarily behave at all frequencies the way we think they do. And so that's another one that is important to keep in mind. Before we get there, I wanted to go to our class and then with you review the last exercise, which you guys had up until, in fact, I did not even close at 9. It took much longer, but until 9 p.m. And I wanted to show you what I saw. And we wanted to discuss that a little bit.
Now it's closed, right?
Now it's closed. Exactly. So this is the last problem that we had. And let me, these are the correct answers. So correct answers. And these are the number of people on the side that answered that accurately. So 19 people out of a total, I believe we had of 58. You can see to the left, it says 58 out of 65.
Professor, I had a real quick question regarding circuit A. So at DC operation, it's just RS connecting V in to V outs.
Mm-hmm.
So I said it wasn't low pass just because it's dependent on the load. I just thought, well, this is the only circuit we have, so assume the load is 0, then it's not low pass.
Well, excuse me, wait. Circuit A, when omega goes to 0, it has a resistor RS.
Right.
So there is DC that goes to the resistor. Through the resistor goes to the other end.
Right.
Can you show the answers again?
But I guess potentially not very much.
It does not matter, but there is DC that goes through, because how do you know how much your RS is?
Can you scroll down a little again?
Scroll down. Where do you gonna look at? Do you see that?
The answer, sorry for
The answer. The answer is all pass. And I would like to explain why. The way it is. First of all, when omega goes to 0, CP, CDS1, and CDS2 are all open circuits. And L is a straight wire, behaves like. So you have a resistor RS, and there is DC that goes through the resistor. Second, when omega is very high, your CP is like a short, your CDS1 is like a short, your CDS2 is like a short. So you have 2 resistors in parallel. So there is still DC that goes through. Okay, so that's what you get there. The second one is when CP, when omega goes to 0, CP is like an open. And so you have L is like a wire, behaves like a short. And then so you have an RS with one in parallel, RDS1 to the left, RDS, RI to the right. Then, okay, so that's a low pass. When it's, that goes low. So when CP is a high, when omega is high frequency, CP is a short. CDS1 is a short. CDS2 is a short. So nothing goes through to the load. So that is like, therefore, a low pass filter. We go to the next one. C. When frequency omega is 0, CP is an open, CD1 is an open, and CS2 is an open. So practically you have a short at L a short and LD2 and short and LD1. So practically this is like nothing goes through, all right, because it's shorted at the end. When frequency is very high, CP is shorted, CS2 is shorted, CD1 is shorted. So in any case, even if you don't look at the front, you have a short at the end, so it's 0 at omega high. However, as we discussed, and as you have seen from circuits, whenever you have an LC, whenever you have inductors and capacitors, a circuit like that shows a resonance or more. So that will make it a bandpass filter. All right, so it's 0 at both sides, and it's like it has a resonance or more somewhere in between, so it's a bandpass filter. Maybe not a good one, but it does pass something in the middle. And then the last one, D, when frequency is 0, LP is like a short, LD2 a short, LD1 a short, so that is 0. And then when L is very high, then practically I would say, well, I called it a high pass. In that case, you can argue that L is going to be a very high resistance, but it's going to be there. So practically, you can argue this is going to be a high pass. It could also be the last one, and so you have all inductors. It cannot be an all stop, but it's going to be a high pass filter, practically because you have a resistor R sub S. And then, yes, you have an inductor, but it's going to add to the resistor, then something is going to go through. So the two LD1 and LD2 going to the ground, they will be very high. So practically from there, and the values they have, they're not going to see, there is not going to send through very much. And the same thing through LP. So that's what, the last one probably was the most tricky. But the other two, I was thinking the 19, which was 27, 6, and 19 for the last. So,
Professor?
yes.
For number 3, the spelling of the bandpass, there were 2 different bandpass answer selections. One of them had a dash and the other one didn't. And it looks like the one without the dash was the correct answer. So I think you would have a lot more correct answers for number 3 if both the bandpass.
I can change that and I can check it out.
I was pointing that out.
Yeah, thank you. Thank you. In fact, thank you. Thank you for telling me this. When I go and change it, it's gonna correct everything. So it does that automatically, all right? So if I change the answer.
Dr. Katlili,
Yes.
it's a band pass for the reason it doesn't pass anything when the frequency is either low or high, right? For
Yes,
C.
but there's a resonance in between. So whenever there is a resonance, there is either a band pass or a band stop. But since it's 0 on the two ends, it cannot be a band stop. It's not going to stop anything. It's going to be a band pass. Okay?
Do you mean only when there's an inductor and capacitor parallel?
Yes, whenever you guys, here is what I have. Absolutely. So whenever there is an inductor and a capacitor, you have a resonance. And so if you go to your circuits, when you do the RLC, that's where you find the resonances of a circuit. Every time you have an L and every time you have a C, you have to have both of them. Then you have a resonance. You don't know where the resonance is unless you go and do the calculations. You don't know how high it is at resonance until you find the calculations, especially since you have resistors in there and may change the up and down of the resonance. But you know that there is a resonance in a circuit like this, always. And if it starts at 0, then the only way for the resonance to go is up. So it's bandpass. If it starts high, so if it's high at the low end and if it's high at the high end, it can be both a band pass or a band stop. But if it starts at 0 on both sides, it can only be a bandpass. Now, I know I would say the 3 and 4 would be the most challenging, and I expected there to see some problems, but for 1 and 2, I expected something better. And the reason I'm sharing this with you is we're going to do a lot of this. I will give you more of this, because if you will see later, the only work that you have to do in this class to develop a low noise amplifier or a mixer or with the exception of filters, a filter even, or to be able to put them together, is to know how to do the matching. That's all. An amplifier is one or more transistors, say even the simplest case is one transistor. It can be a low noise amplifier, or it can be a high power amplifier, and the only difference is how you match it. How you connect, of course, I mean, it depends on the difference of the transistor, but one transistor can behave in one way or another depending on how you do the matching. And if you don't know how to do matching, and if you don't know which one brings the DC in and which one does not bring a DC, then you cannot do any of this. So matching, either with transmission lines, we're in high frequency, so you will see that we will use transmission lines for the matching, because there are not too many good quality lumped elements. But matching and knowing which circuits take DC through and which circuits do not take the DC through is absolutely critical. Very important.
Can you go back to circuit A and B? I still don't understand
A
why.
and B. A and B. That one. Okay. Low frequency. When omega goes to 0, what happens to CP becomes, let me in fact do it also. Okay, so let me in fact, I cannot write on this one. Let me see. I need to, let me copy it on a piece of paper and then I will, so I can write. CP here. 1 second. Okay, let me try to solve this one, all right? Here, I'll do it on this side. The circuit we have is one capacitor here, one inductor, a resistor, L, say, and R, and then this is CP, and then here we have CDS1. These are all parasitics, the other ones. RS1. CDS2, RS2. Okay, so when omega goes to 0, what is CP? What is creating? 1 over omega CP. You remember that? That's an impedance, the equivalent impedance of the capacitor. That goes to infinity. So it's open circuit. Open circuit. The same thing happens to CDS1, CDS2. So practically what I have here is this is gone. This is gone. This is gone. So what do I have in there? I have an L has practically become very small. So what do I have in there? I have this circuit. Does DC go through?
Yes, it goes through that.
Okay. Now let's assume, go back and create the same circuit. So we have this one here. Okay. When omega goes to infinity, what happens to CP that goes to 0? Okay.
Short.
Huh? Yes.
Short.
Short, yes. So it becomes a short. So here, and I have that. And then also it becomes a short down here. And down here. Okay, so this looks, how does this look like? Looks like this. Does DC go through?
Yes.
Yes. Not DC, excuse me, high frequency. Does it go through?
Yes.
Yes, because it's gonna be like that, okay? So practically that passes all frequencies.
So you're only looking at what passes through those two nodes, like the two
Yes.
circles in the circuit. If it passes through that,
Yes.
then
The
okay.
2 nodes of the circuit is between here. Sorry. This is the capacitor here. This is the capacitor here. Let me show you. And the capacitor set. These are the 2 nodes here. So you see what happens when it goes from A to B, from A, here capital A is A to B.
So if there's a capacitor and an inductor here, why isn't bandpass being considered for this circuit?
Where is the inductor? Oh, the capacitor is open, though, in this particular case. You mean this
It's
one,
2
why
o'clock.
there is not a band pass? Okay, so in this particular case, the capacity, this one, if you remember from your homework, this is the equivalent circuit of the inductor. And the capacitor, you can call that, it's gonna go past all of it. What is gonna happen, I mean, the fact that all of the frequencies go through, it makes it an all pass, and in an all pass, it does not necessarily mean it's gonna be, an all pass does not mean that it's gonna be all a flat line. An all pass may have resonances, all right, but at least allows the frequencies to go through. The reason we are talking about the resonance when it's 0 here and here, if there is only C or L alone in the circuit and it's 0 here and 0 there, then it's 0 in between. But if there is L and C in this
Professor, there's something wrong with your internet.
Professor, we're having connection issues to you, it appears.
Can I suggest that I log off and log on again? So don't go anywhere until I come up again, just to see in case it's me. But wait for a second, wait, and I will log off and come back again.
We can see you now.
You can see me, yeah.
See and
Can you
hear.
hear me?
Yes.
Yes.
Everything.
Now it's
Okay.
as normal.
Now it's clear. Let me see. Okay, let me, what do I need to do? To go here, go there.
Yes.
Okay, perfect. There is kind of, say Zoom has a problem. It's not me. Because the Zoom could not recognize my microphone or something. Strange, but it's been misbehaving last few days.
Professor, it's happening again.
Okay, we're going back to it's happening. Okay. Let me stop this one then. Stop.
You're muted if you're trying to talk, Professor. Yes.
Yes.
Okay, there is this, it gets me with this Zoom error for some reason. But what I will do, then I will try to talk about this without drawing, and then I will, there is a problem. I don't know what the problem is, however, to tell you the truth. Because, why do I have a problem when I get the iPad? But I don't want to stop the class, and what I will do is, and then try to connect. I would like to talk about this, and then I will give you I will show you the solutions. I will share here from the, okay. You can see, I need to share okay, share. Did you see that or not yet?
We can
We
see
see
it.
this one now.
Okay, perfect. So what I was gonna say is that if a circuit like this one, this is your input port.
Can you guys still hear me?
No, I got nothing either.
Do you see the pointer here?
Yes.
It's better now.
Yeah, okay. There is a Zoom problem, I have to tell you. I just have a Zoom problem here. I don't know what to do with that. If it happens again, I will reconnect. But here, or maybe I will connect only on the other one. Anyway, this one, let me do this until it has a problem. This one here, input and output. And if you have something going through, it's an all pass. An all pass filter does not necessarily mean it's going to pass everything at the same level. Can you hear me? Just want to check.
Yeah.
Yes.
Okay, perfect. So an all pass filter does not mean that it's going to pass everything at the same level. I mean, it's a good filter, it has to. If it's not a good filter, if it's just a circuit like this, well, the only thing you want to know for circuits like that, these are not filters. These are just circuits. You want to know, are they going to pass DC? Important. Are they going to pass any higher frequencies? That is important because sometimes you want to, many times when you do circuit design, you want to stop the DC unless you need it, and you want to stop other high frequencies that come out of noise. A lot of times noise is either DC, offset, usually DC offset, or it can be a high frequency noise. You wanna stop both of those, all right? Or at least you wanna know. You wanna know, so in case that happens, then you know that you have to create either a low pass to avoid high noise or a high pass to avoid the DC after your circuit. As a matter of fact, this is a high frequency equivalent circuit for an inductor. So yes, you have a CP, which is a parasitic capacitance, and you have an L, which is primarily your primary inductance. And yes, it's going to show a resonance because CP is very small, and L is your inductance, the 1 over square root of LC, which is your resonant frequency, is going to be very high, hopefully outside. This is something I wanted to speak with you today. So your inductors and your capacitors do not necessarily in high frequencies look like a simple inductor and a simple capacitor. They have all of these parasitics. CP is a parasitic, CDS1 is a parasitic, RDS1 is a parasitic. These are Can you hear me?
Now we can.
Now we can.
We hear
Okay,
you now, but it's
I will log off. Don't in case that you are dropped off, try to connect again. Let me just do this for a second. 1 second. I'll get I'll stop sharing and then I'll get off the Zoom.